Good morning, students. In our previous video we had discussed how to find the fundamental solutions of the Laplace equation. In this we will solve a question to find the fundamental solution for a Laplace equation with boundary conditions. Now let's see the question. If u be a harmonic function in the interior of a rectangle 0 to a and y belonging from 0 to b in the xy plane satisfying Laplace equation. This was our Laplace equation, del to u by del x square plus del to u by del y square is equals to 0 with boundary conditions. There are 4 boundary conditions. U0y is equals to 0, uay is equals to 0, uxb is equals to 0 and ux0 equal to fx. Obtain the solution of the above problem. Now we have to find the solution of the above problem with these 4 boundary conditions. So we'll take the Laplace equation as equation number 1 and first 2 boundary conditions as second and the last 2 boundary conditions as the third. Now we had obtained the fundamental solution of the Laplace equation, and it was which we had obtained in our last video was uxy equal to ax plus b into cx plus d, or uxy was equals to a e to the power mu x plus b e to the power minus mu x into c cos mu y plus d sin mu y, and uxy was equal to a cos mu x plus b sin mu x c e to the power mu y plus d e to the power minus mu y. Now we'll apply the boundary conditions over these solutions and we'll try to get the solution of the problem. Now applying these 2 boundary conditions in our first solution, that is applying 2 in equation 4, we get uxy equal to ax plus b cx plus d. Will put 0 y and will put the value as 0. So the value of x is 0. We'll put the value of x as 0. We'll get b into, this is cy plus d, sorry. We'll put x 0, then this comes b into cy plus d, and we'll find we have in our question we had use 0y equal to 0. We'll put the value of u 0y, that is equal to 0, is equals to b cy plus d. Now these 2 product gives us 0, then either of them can be 0, but cy plus d will not always be 0 because the condition says that the x term is 0 and it does not contain any x term. So b will always be 0 and cy plus d is non-zero. Now our second condition was uay equal to 0, and we'll put uay in place of x, we'll put the value a, and this is again equal to 0. So we get that either a small a is equals to 0 or cy plus d is equals to 0. Again cy plus d cannot be 0, then a is equals to 0, which gives us as small a being the constant, this is non-zero, then a is equals to 0. Sorry, small a is a constant from the boundary condition, so this can't be 0 and a is equals to 0. From here we got b is equals to 0, and from here we got a equal to 0. Both of them are 0. If we'll put a and b both as 0, this whole solution becomes 0 for all the conditions, and hence it becomes invalid and hence it is rejected. Now we'll put again these boundary conditions over our equation number 5 and 6, which were our other solutions to the Laplace equation, and we'll try to find the solution of the problem. Now we'll put the boundary conditions in equation number 5, which was our second solution to the fundamental solutions of Laplace equation, and we get u0y equal to a plus b c cos mu y plus d sin mu y. Our second solution was uxy equal to a e to the power mu x plus b e to the power minus mu x into c cos mu y plus d sin mu y. So we'll put 0 in place of x and y as it is, so we'll get e to the power 0 and e to the power minus 0, which becomes 1, and we simply get as 0 equal to a plus b c cos mu y plus d sin mu y. Now these 2 product gives 0, either a plus b is 0 or c cos mu y plus d sin mu y is equals to 0, and this can't be 0, so a plus b is equals to 0, which gives a equal to minus b. Now we'll put another boundary condition, uay equal to 0. Now uay equal to, in place of x we'll simply put a and the y as it is, and on solving we will put a equal to minus b. So the value of b is replaced by minus of a and a is taken as common. Now these three product again gives 0 because the second boundary conditions was uay equal to 0. Either a is equals to 0 or this, but these two can't be 0 because these two are constant and one is containing y. So a is equal to 0, and since a is equals to 0, b automatically becomes 0. So the equation 5 again is discarded because the whole solution becomes 0. So we'll discard again equation solution number 2, and we'll come to the third solution, which was our equation number 6, and we'll put the boundary conditions in the third solution. And our third solution was uxy equal to a cos mu x plus b sin mu x into c e to the power mu y plus d e to the power minus mu y. And in this we'll put all the four boundary conditions. The first boundary condition was u0y equal to 0. On putting this simply becomes cos 0 is 1 and sin 0 is 0. So we get a e to the power mu y plus d e to the power minus mu y, and we'll put the value of u0y equal to 0, and we get a into c to the power mu y plus d e to the power minus mu y. These two product again give 0, so either a is equals to 0 and this can't be 0 again, so a is equals to 0. Now we'll put the second boundary conditions, which was uay equal to 0, and we'll place a in place of x. So uay becomes a cos mu a plus b sin mu a into c to the power mu y plus d to the power minus mu y, and we find the value uay from the boundary condition. It was 0, and this becomes b sin mu a because the value of a we had obtained as 0, so we'll put it as 0. So this simply becomes b sin mu a into c e to the power mu y plus d e to the power minus mu y. Then these three product again give 0. Either b is 0 or this, but b can't be 0 because as soon as b becomes 0, then a and b again both will become 0 and the solution will get discarded. So b can't be 0, and sin c e to the power mu y plus d e to the power minus mu y can't be 0. Then sin mu a is equals to 0, which gives mu a is equals to n pi, and mu is equals to n pi by a. So we have obtained the value of mu is equals to n pi by a, and we'll put it in our equation number 6. Then we get uxy equal to a cos n pi by ax plus b sin n pi by ax into c e to the power n pi by ay plus d e to the power minus n pi by ay. And now we'll put the value a equal to 0, which we had obtained earlier. So it becomes uxy equal to b sin n pi by ax into c e to the power n pi by ay plus d e to the power minus n pi by ay. Now we'll put the third boundary condition, which was uxb equal to 0 in this. So we'll put b in place of y, and simply y is replaced by b. On solving we get b sin n pi by ax c to the power n pi by a into b plus d e to the power minus n pi by ab equal to 0. Either b is 0 or this, then b becomes non-zero, and n pi by ax was non-zero because we had equated it and obtained the value. And then this becomes c e to the power n pi by a into b plus d to the power minus n pi by a into b equal to 0. And on solving we get the value of c is equals to minus d e to the power minus n pi by a into b by e n pi by a into b. So uxy becomes, now we'll put the value of c in our solution, which we get equal to sin n pi by ax. C is replaced by minus d e to the power minus n pi by ab e to the power minus e to the power n pi by a into b into e n pi by a into y plus d to the power minus n pi by a into y. And on simplification we get, now this is written as, this is minus e n pi by a into y minus b. This, the bases are same, products are being added, and then this simply becomes, on taking the LCM, this gets multiplied to this, and again we get minus n pi by a. This is minus y plus b, so this becomes and taking minus as common we get y minus b here. Now we'll rearrange the terms. this comes over here, e and pi by a, and minus gets multiplied, b minus y, and this minus and pi by a, b minus y, again minus is taken common from here. So this becomes the sine hyperbolic e to the power x minus e to the power minus x by 2, which gives sine hx. So e to the power x minus e to the power minus x will give us 2 into sine hx, and this has been replaced by 2 into sine hx, and x was our n pi by a into b minus y, and this was simply cn is another constant, bd is replaced by cn. So we find the general final equation as un xy is equals to 2cn sine n pi by ax, and this comes to the numerator, e minus n pi by a into b sine hyperbolic n pi by a b minus y. Now we'll simply put the value of 2cn e to the power minus n pi by a into b as dn. So our solution becomes un xy equal to dn sine n pi by ax sine hyperbolic n pi by a b minus y. Now to find the fundamental solution uxy, the summation runs over n equal to 1 to infinity un xy, and we get uxy equal to summation n equal to 1 to infinity, and we'll put the value of un xy, which was dn sine n pi by ax sine hyperbolic n pi by a b minus y. Now we'll put the fourth boundary condition, which was ux0 equal to fx. So ux0, so the value of y will be equal to 0. ux0 is equals to summation n equal to 1 to infinity dn sine n pi by ax sine hyperbolic n pi by a into b, and y is 0. So ux0 was equal to fx as per our boundary condition. So fx becomes summation n equal to 1 to infinity dn sine n pi by ax sine hyperbolic n pi by a into b. Now this is a half range Fourier sine series of fx in the interval 0 to a, where dn sine hyperbolic n pi by a into b is equals to 2 by a 0 to a fx sine n pi by ax dx, and dn can be simply obtained by equating this. So sine comes to this side, and we get 2 by a sine hyperbolic n pi b by a integration 0 to a fx sine n pi by ax into dx. So this was our solution to the problem.